This video follows right along with your Chapter 4, Section 2 lecture notes. We will continue solving systems of linear equations, and in this lesson we will talk about how to do that with the substitution method. To solve a system of equations by using the substitution method, we will first solve one of the equations for one of the variables, and then substitute that expression for the variable in the other equation. Let's look at an example. In example 1, we have this system of two linear equations. Notice that the first equation is already solved for one of the variables. It's solved for x. To use the substitution method, we will use the fact that x is equal to 3 over 4y plus 5 and substitute that for x in the second equation. So instead of 8 times x minus 5y equals 28, we have 8 times 3 over 4y plus 5. Notice that now we have an equation with a single variable. That means we can solve for y. First, we need to distribute the 8 to both terms inside the parentheses. We have 8 times 3 over 4y plus 8 times 5 minus 5y equals 28. We can simplify 8 times 3 over 4 by noting that 4 goes into 8 2 times and 4 goes into 4 1 time. So this becomes 2 times 3 or 6y, and 8 times 5 is 40. Combining like terms, we have 6y and negative 5y. That simplifies to 1y. Finally, subtracting 40 from both sides, we find that y is equal to negative 12. Now that we know that y is equal to negative 12, we can substitute y equals negative 12 here and solve for x. So we have x equals 3 over 4 times y, which is negative 12, plus 5. Simplifying 3 over 4 times negative 12, we note that 4 goes into 4 1 time and 4 goes into 12 3 times. So this becomes x equals 3 times negative 3, or negative 9 plus 5, or x is equal to negative 4. Now we have that x is negative 4 and y is negative 12. We have the ordered pair negative 4, negative 12, and that's the solution to this system of equations. Let's look at example 2. In example 2, we are going to again use the substitution method, but notice that we will have one extra step. In example 1, we already had an equation that was solved for one of the variables. This time we don't have that, so we will need to do that first. Let's take this first equation and solve for y. If we subtract 3x from both sides, we have negative y equals negative 3x plus 19. Multiplying both sides of the equation by negative 1 will give us a positive y equals positive 3x minus 19. Now that we've solved for one of the variables in one of the equations, we will substitute for that variable in the other equation. So we'll have 2x plus 5 times y, but we know that y is equal to 3x minus 19, and this is all equal to negative 10. Simplifying this equation, we can solve for x. First, we'll distribute the 5 to both terms inside the parentheses. This gives us 2x plus 5 times 3x, or 15x, plus 5 times negative 19, or negative 95. We have a positive 2x and a positive 15x for a total of positive 17x. Adding 95 to both sides, we have 17x equals 85. Finally, dividing both sides by 17, we have x equals 5. It's tempting to stop here since we've solved for x, but remember that a solution to a system of two equations with two unknowns is an ordered pair x, y, not just a single value for x. But now that we know what x is, we can substitute that back into this equation and solve for y. That gives us y equals 3 times x, which is 5, minus 19. 3 times 5 is 15, so this is y equals 15 minus 19, or y equals negative 4. Now we have our solution, the ordered pair 5, negative 4, and we've solved this system of equations. Let's keep going on to example 3. In example 3, we're once again going to solve this system of two linear equations using the substitution method. Notice how our first equation is already solved for y. So we can simply substitute that right in place of y in the other equation. We'll write this as 4x plus 2 times y, but in place of y, we will write that y is equal to negative 2x plus 5 from the first equation. Distributing the 2 to both terms inside the parentheses, the left side of our equation becomes 4x minus 4x plus 10 equals 7. Positive 4x minus 4x is 0, so this becomes 10 equals 7. This, of course, is not a true statement. It's never true. That lets us know that there are no solutions to this system. Let's take a closer look to see why this system has no solutions. Our first equation was already solved for y, so we can see that it has a slope of negative 2 and a y-intercept of 0, 5. The second equation is not solved for y, but we could do so. Subtracting 4x from both sides, we have 2y equals negative 4x plus 7. And dividing everything by 2, we get y equals negative 2x plus 7 over 2. That means that the second equation has a slope of negative 2 and a y-intercept of 0, 7 halves. These two lines have the same slope and different y-intercepts. We have a pair of parallel lines. They will never intersect, so there's no solution to this system of equations. Now we'll look at example 4. We need to first solve for a variable in one of the equations. Notice how this x isn't isolated, but at least it doesn't have a coefficient. So that will be our easiest variable to solve for. Subtracting 3y from both sides, we have x equals 9 minus 3y, and we've isolated one of the variables. Now we can substitute that in for x in the other equation. So instead of negative 5 times x, we will write negative 5 times 9 minus 3y. Let's simplify and solve for y. Distributing the negative 5 into the terms in the parentheses, we have negative 5 times 9, or negative 45. Negative 5 times negative 3y is a positive 15y. We have a positive 15y and a negative 15y that simplify to become 0. This leaves us with negative 45 equals negative 45. Notice at this time we ended up with a statement that is always true. That means that we will have an infinite number of solutions. This is different, however, from having the solution set be all real numbers. That's not the case here. We will have an infinite number of solutions, but not just any point. Let's take a closer look at these equations and see why this is happening. We'll start with our first equation, and let's solve for y. Now we'll do the same for the second equation. When we solve each of these equations for y, we find out that they were really just two expressions for the same line. So every point that's on one line is also on the other line. In our last lecture video, we defined this as a dependent system. And with a dependent system, we need to express our solution set as all ordered pairs that lie on this line. We can write these ordered pairs as x, comma, negative 1/3 x plus 3. Notice that this is the same as writing xy, but in place of y, we substitute what we know y is in terms of x. That is, the y value depends on the value of x. Let's head over to example 5. In example 5, we will once again use the substitution method to solve this system. Notice that in our two equations, none of the variables are isolated and all of the variables have a coefficient. So it's dealer's choice which variable we want to solve for in which equation. Let's simply take our first equation and solve for y. We'll subtract 3x from both sides, giving us 2y equals negative 3x plus 13. Dividing everything through by 2, we have y equals negative 3/2 x plus 13 over 2. Now that we've isolated a variable, we can substitute for that variable in the other equation. When we do that, we have 4x minus 3 times negative 3/2 x plus 13 over 2 equals negative 28. When we distribute the negative 3 to both terms inside the parentheses, we have 4x minus 3 times negative 3 over 2, which is positive 9 over 2x, plus negative 3 times 13 over 2, or negative 39 over 2. And this is all equal to negative 28. What's different about this example is we have some fractions involved, and that can happen when solving systems. What we can do to get rid of the fractions is clear them using the least common multiple of the denominators. Since in this case all of our denominators are 2, we can clear them by multiplying both sides of the equation by 2. Distributing the 2 to every term, we have 2 times 4x, or 8x, plus 2 times 9 over 2x, or 9x, plus 2 times negative 39 over 2, or negative 39, equals negative 28 times 2, or negative 56. Now we no longer have those fractions. On the left side, we can combine like terms. Positive 8x and positive 9x is a positive 17x. And adding 39 to both sides, we have 17x equals negative 17. That gives us x equal to negative 1. Now that we know that x is negative 1, we can substitute that back into this equation and solve for y. We have y equals negative 3 over 2 times negative 1 plus 13 over 2. Negative 3 over 2 times negative 1 is positive 3 over 2, and 3 over 2 plus 13 over 2 is 16 over 2. Now we know that y is equal to 8. And for our solution, we have the ordered pair negative 1, 8. And we've solved this system of equations. Let's finish up this lesson with an applied problem. We have here that adults are charged $8 and children are charged $4 to attend a fundraising dinner. If 112 people attend the dinner and $788 was raised, how many adults attended? Let's start with the fact that 112 total people attended. If we let the number of adults that attended be the letter A and the number of children that attended be the letter C, we can write the equation A plus C equals 112 for the total number of people that attended the dinner. We also know how much money was raised, $788. Each adult ticket cost $8. So the amount of money raised from adult tickets is 8 times A. Children's tickets cost $4, so the amount of money raised by selling children's tickets is 4 times C. Adding those two values together gives us the total amount of money raised. So the sum is $788. Now we've created a system of two linear equations and we can solve them. Let's start by solving the first equation for one of our variables. We can solve for C by subtracting A from both sides. We get C is equal to 112 minus A. Substituting that into our second equation, we have 8A plus 4 times C, but C we know is 112 minus A. Now we can solve for A. Distributing the 4 into the parentheses, we have 8A plus 4 times 112, which is 448, plus 4 times negative A, or negative 4A. Combining our like terms of positive 8A and negative 4A, we have 4A plus 448 equals 788. Subtracting 448 from both sides, we have 4A equals 340. That lets us know that A is equal to 85. In other words, the number of adults that attended this dinner was 85. And we've solved this problem. That concludes this lesson on solving systems of linear equations.